Now in this video lecture we will go through the electronic configuration of copper, right? In the previous video lecture we have seen how electronic configuration of chromium was different than usual, right? What was the usual configuration? This was the usual configuration, right? This was the usual configuration, wherein in the usual configuration this s orbital has 2 electrons, right? And there are 1 2 3 4 electrons in the d or in the d subshell, right? In these d orbitals we have 4 electrons, right? So what we did to achieve stability, one electron from s orbital, right, shifted to this d orbital, right, to form d5 4s1 electronic configuration, right? So now after shifting one electron from s to d orbital, we have maximum number of unpaired electrons, right? Or more, or what we say is, on transferring electron from s to d orbital, now we have more symmetry, right, compared to before. If you look at this is the configuration. Now it looks more symmetric, right, because all the orbitals are equally filled with electrons, right? So this looks less symmetric, this is more symmetric, right? So due to symmetry, we know that symmetry adds to the stability, right? It adds to the stability of the atom. So that is why this is more stable, right? d5 4s1 is more stable compared to d4 4s2, right? And the other reason was, when you have electrons, right, with parallel spins in the orbitals, these electrons can exchange, right? These electrons can exchange their location, right? It's like if you look at this can exchange its position with this, right? So it can exchange its position with 4 other positions, right, or with 4 other electrons. Similarly, this one can exchange its position with 3, this one with 2, right, and this one with 1, right? So total here is 10. So 10. If you look at this, total exchanges would be, this can exchange 1 2 3. For this one it can exchange with this, right, or with this, so 2, and this one it can go here. This one it can exchange with this one, so 1 here. Here total number of exchanges are 6, here total number of exchanges are 10. So more exchanges means more release of energy. More release of energy means you have more stability, right? So that is the reason more are the number of unpaired electrons in the d orbitals, more symmetric it is, and due to more number of unpaired electrons with parallel spins, these are unpaired electrons, right, in each of the orbitals, d orbitals, with parallel spins, right? All these have same spin. If you can see, all the arrows are pointing upwards, so we say all these electrons have parallel spins, right? So in the second case we have more number of exchanges, right? And we know that energy is released during exchange, right? And these are degenerate orbitals, right? And electrons with parallel spin, right, present in degenerate orbitals tend to exchange their position, right, like I said. So the number of exchanges taking place is maximum when the degenerate orbitals are exactly half filled. When we shifted the electron from 4s to d orbital, we have maximum number of half filled orbitals, and with these maximum number of half filled orbitals we have maximum exchanges, right? We have maximum exchange of positions, right? So maximum exchange of position means more energy is released, right? So more energy released means more stability. Right, now let's quickly look at the second one, which is your copper, right? Copper has this copper has atomic number 29. So let's look at its electronic configuration. It would be 1s2, right? 2s2, right? Then you have then you have 2p6, right? This is 2px, 2py, 2pz, right? Then you have 3s2, right? And after this you have 3s2, then you have 3p again, 3p orbitals, right? Like this. You have, we are following Pauli's exclusion principle by putting arrows up and down, 3px, 3py, 3pz, right? Then you have 3d. D, we know in d orbital we have, sorry, in d subshell we have 1 2 3 4 5 orbitals, right? For 5 orbitals means we have how many electrons? 10 electrons, right? So here you have 3d orbitals, right? And this is 3d xy xz, right? Yz, then 3 z square. These are the orbitals of d subshell, right? And if you want to fill it, these 3d orbitals, you have right, it has one half filled orbital. This d subshell has one half filled orbital. Then you have, after 3d, you have 4s, right? 4s has 2 electrons. Now just count the total number of electrons: 2, 4, then 6, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Total of 29 electrons, right? The atomic number of copper is 29. Now this electronic configuration we say is not much stable, right? Why? Because we said that half filled, completely half filled, or completely filled, right? Completely filled or completely half filled orbitals have maximum stability. Why they have maximum stability? Because completely filled or completely half filled orbitals have more symmetry, right? So more is the symmetry, more is your stability. So what we will do is, in order to make this d subshell, the orbitals of d subshell symmetric, we will transfer one electron from this 4s orbital to 3d orbital, right? So what we are basically doing is, we are transferring electron from orbital of higher energy to orbital of lower energy to orbital of higher energy, right? And this is an exception to Aufbau's rule, right? Because Aufbau's rule says that electrons should be filled in increasing order of their energies, right? Last electron will go to the orbital of highest energy, right? But here we are doing reverse of Aufbau's principle. What we are doing is, we are transferring electron from orbital of higher energy to orbital of lower energy, right? And we are saying that this adds to the stability, right? Now this much of electronic configuration will remain same. Now let's look at this electronic configuration will change, right? 3d orbital and 4s orbital electronic configuration will change. right? We will transfer electron from 4s orbital to 3d orbital, right? So it would look like this. This will remain as it is, right? Now earlier in this case the number of electrons in this orbital is 1, right? So when we transferred one electron from orbital of higher energy to orbital of lower energy, this is how it will look like. And now we have only one electron in 4s orbital. Now 4s orbital is half filled, all these orbitals are completely filled, right? So we said, so this completely filled set of orbital, right, d subshell, this looks more stable, this looks more symmetric, right? This looks more symmetric, right? And more symmetric means more stable, more stable. That means this electronic configuration is more stable, where we have 1 2 3 4 5 3d 10 4s1 configuration. This configuration is more stable compared to 3d 9 4s2 configuration, right? Why? Because of more symmetry, because of high symmetry we have more stability, right? So this is the reason. And the second reason is your exchange energy, like we have discussed here. In this case, in the case of chromium, right, when we shifted electron from this s orbital to this high energy orbital, right, this d orbital, sorry, from high energy to low energy orbital, so when we transferred it, this became more symmetric. And the second thing was the exchange energy, right? There was a concept of exchange energy that we discussed, right? Exchange energy. What is exchange energy? This is the energy released when these electrons can change their position, right? Now we have more unpaired electrons, all the orbitals are half filled. Now all these orbitals, right, can exchange, the electrons in these orbitals can exchange energies with other orbitals, right? Like this one, this can exchange energy, this can exchange position, this electron can exchange its position with this, right? And this one can exchange position with this, right? So after we have one more electron in this orbital, the number of exchanges increased. So when there is an exchange, energy is released. So more exchanges means more energy will be released, so more stability. Same is here. We said that the number of exchanges, right, is more in completely filled or half filled orbitals. Now all these are completely filled orbitals, right? So now they can easily exchange positions, right? So we have more completely filled orbitals after shifting electron from 4s to 3d orbital, right? So more exchanges means more energy will be released. More energy will be released means we have this atom would be more stable, right? So basically there are two reasons for increase of stability in these exceptional cases that does not follow Aufbau principle. The first one was more symmetry, right? More symmetry means more stability, right? And symmetry is achieved by shifting electron from 4s orbital, which is of higher energy, to an orbital of lesser energy, right? Which is an exception to Aufbau principle. Second is exchange energy, right? Now we know that exchange energy is maximum when we have all orbitals completely filled or all orbitals half filled. So more exchanges means more exchange energy, more exchanges means more energy would be released. Energy released will be greater when exchanges are more. What exchanges we are talking about? Exchange of the position of these electrons with one another, right? Because when exchange takes place, right, between two orbitals, energy is released. So more exchanges means more energy would be released. More energy would be released means the atom is more stable, right? So this is it. Now there is one small thing that we need to consider here is about electronic configuration, right? What is the need of electronic configuration? Electronic configuration, right? What is the need for electronic configuration? Right? Electronic configuration, this electronic configuration was finalized, right, after we finalized the model of atom, that is wave mechanical model of atom or quantum mechanical model of atom, right? So after the model of atom is finalized, now we have the electronic configuration based on the concept of orbitals that we have done in wave mechanical model of atom, right? And we have done all the rules in the previous lecture that we need to consider, right, while writing the electronic configuration. Now what is the need of electronic configuration? There were a lot of questions that are in the minds of scientists, like why do atoms combine to form molecules, right? Why inert gases like helium, neon, argon, krypton, xenon, radon are not reactive, right? There are many chemical properties of elements, why some are metals, why some are non-metals, right? So all these were answered by the electronic configuration, right? Like we say that why atoms combine to form molecules, because the atoms that have unstable electronic configuration, right, that do not have 8 or 2 electrons in the outermost shell, those type of atoms are less stable and they will react, right, to make 2 or 8 electrons in their outermost shell, right? Now what are metals and non-metals? Elements that have 1, 2 or 3 electrons are metals, right? How do we know that they have 1, 2 or 3 electrons in their outermost shell? By writing their electronic configuration. And those that have 5, 6, 7 electrons, they are non-metals. Same we get to know after writing the electronic configuration, right? And why helium or other noble gases does not react? Because they have completely filled orbitals, doublet or octet, right? That is, they have 2 electrons or 8 electrons. So their octets are satisfied, so they will not react. How we check that their octets are satisfied? By writing their electronic configuration, right? And halogens like chlorine, bromine, right? All these are fluorine, chlorine, bromine, iodine, all these are very reactive. Why they are reactive? Because they have 7 electrons in their outermost shell and they can easily accept 1 electron to form a chemical bond. So they are more reactive, right? So all these things are answered by electronic configuration, right? So that is why electronic configuration is needed and is important, right? So I hope all this is clear to you. Just remember this, right, while writing the electronic configuration, and just know that these two, copper, electronic configuration of chromium and copper, is an exception to of Bohr's principle, right? Thanks.